like these four like fundamental like features like guaranteed messaging passing and scale out ability, and also it's fault tolerant. Also like just like any other like computing framework, they abstract all the like failure handling and the scaling problems from the users so that our users can focus on their core logic, business logic to develop their apps. So this is briefly about Twitter Storm. So next thing is we want to like discuss about some kind of problems we encountered when we are operating Storm within Twitter, and that's kind of the reason why we choose to develop Heron. So the first thing is we can look at the Storm structure. So basically it's a very classical, typical coordinator and a worker mode. Here the Nimbus is like the coordinator, right? So it's responsible for a lot of stuff like accepting requests and scheduling jobs and handling failures and doing some metrics things. So that's it plays a very important role in the whole like Storm cluster. And here we have a pool of workers called worker node. It has like supervisor and a bunch of workers. They are responsible for running different tasks assigned by the Nimbus. So the first thing we found is the Nimbus itself is having some problems. Like it has too many like different functionalities packed in one place, so which makes it very complicated. And the second thing is it's kind of a single point of failure. So we experience that some kind of internal topologies, which usually to be very large, like hundreds of megabytes, 400 megabytes jars. Users will take a very long time to submit that whole topology, like hour maybe, to just wait for this job to be submitted and scheduled. And also it doesn't have any like concept of resource reservation or isolation. So all the like user submitted jobs running within one cluster, and they kind of like affecting each other. So that's some things we found. And if we look into the Storm worker, so basically this is a long-running process which we're listening on the network or waiting for the Nimbus to assign like any tasks or jobs to processing. So here, like the one thing is the executor itself is a single process, and within that single process, there are multiple like task or workers task threads. They will like executing different kind of user logics based on the assignment of Nimbus. So the first thing is like every different jobs can like mix with each other. So it makes it really hard to do like debugging when something happens. And also it's also really hard to do the resource isolation to make sure that each job get its own like desired resource requirement, like memory or CPUs for do its own work. And also the hierarchy of the design is kind of complex. And here are some list of other additional issues we encountered when operating the Storm. I would say like nowadays maybe the Storm, since Storm itself is also like evolving and be refining, so some of the issues may be resolved. But at that time, like when we trying to develop Heron, so these are the issues we encountered, and we think it's kind of not good. So I just share this way. The first thing is the lack of back pressure. So Storm basically, if unpredictable like traffic comes, it will like drop in some kind of tuples very randomly. So we don't know what's happening, and the user asks us like why their result is not kind of good, looks weird, and we don't have any insights on that. We cannot find out why. And also there's no kind of workload selection, and also efficiency, especially these efficiencies. So this is some of our production job experience. So I think very simple program, it consumes like 75 cores, and the total topology consumes like 600 cores and 30%. So yeah. And so this is a kind of a discussion. I guess Classic knows more details about it. At that time, like when should we like refine, improve the storm, or we just like create a new one based on the current like operational and maintenance experience and the issues we found. So we choose to do the later one, which is kind of a revolution. So that's why like Heron is built, created. Okay, so now I'm gonna share some knowledge and some brief like architecture design of Heron. The first thing is we have like Heron when we design Heron. So the Heron like has some kind of hard requirements, which the first one it must be like fully API compatible with Storm, because our internal production job at that time there are like over 100, so they're all writing in Storm. So we don't want to we want to like minimize the migration cost of our users. So this is the very like higher priority stuff, and also we want to use the mainstream languages. So I guess you all know, if you worked on Storm, you know that Storm like written in kind of a closure, right? It uses a very special language closure. So it's kind of really hard to find some kind of experts on that and doing some improvement and maintenance on that part of code. So that's why like we choose to use C++, Java, and Python for creating the Heron. And also this one, the task isolation. So I think this kind of it's kind of for modern like applications of computing frameworks. This kind of is also a must-have requirement to separate each job or task so that each one can like running fine without affecting others. And also these are the three other requirements we have, like support for back pressure, so that when some failure cases happens, you can recover like regress-free, not like generating unexpected results or just crashed. And also the efficiency and the batching of tuples requirements. So basically that's kind of the design goals. So here is a very high-level architecture, how Heron is structured. So, so as you can see, like here, it's a list of topologies. So all the topologies, they are totally separated. They will not share any like hosts, any resources together. So each one is just a separate running job, running on top of some scheduling platform. In Twitter, we use Aurora. So all of our jobs are running in Aurora as a list of Aurora instances. And we also have, nowadays, we also have support for Kubernetes and other like young scheduling platforms. So user only needs to use the client CLI to issue the submission command, so that when the topology is submitted to the scheduler, it will be like do all the bookkeeper work, like sync with the Zookeeper for the metadata management and starting all those jobs in the on top of inside the scheduling service like Aurora or Kubernetes. So so now we can look at into like what's inside each one of the topology. So in each topology, there is a special process called the topology master, and also there's a list of containers. So each container is in Kubernetes it's called pod, right? So pod, and in Aurora it's just called container. So each container is a separate resource group containing, which is isolated from other ones. So within each container we have some process called stream manager, and we have a list of separate process called instance or workers. So what happens is when the topology is first started, the team master will write its own like location into the Zookeeper, and within each container, these stream manager, metrics manager, and instances, they will all be started separately, and then the stream manager will read the topology master location from Zookeeper, and then trying to connect to the team master. So once everyone, all the stream managers or all the containers connected to the team master, So the topology master knows where everyone is, so it will broadcast this information to this location information to every stream manager. So that stream manager knows where each other is, and then they will like trying to connect to each other. And then after everyone is connected, then these instances will starting to do their job. So for instance, it's either like a spout or a boat. So that's basically the kind of the big picture of a topology structure here. So, and do you have any? So if you have any questions, just let me know and we can discuss here. So, so before talking about the back pressure, I want to talk a little about how the data is processed or how the data is passing around within a topology. So we can see that we have like 4 containers, right? So each one is one container, and they are connected by the stream manager. So what happens is, for each instance, it will be either a spout process or a both process. So these spout process, they were pulling data from outside messaging systems like Kafka, for example, and the Twitter we have event bus. So once they pull the data from outside, they will like send this to the stream manager. So the stream manager will decide like which where this tuple should be sent, and if it's within if the tuple is meant to be sent, it needs to be sent to some local container or local boat, then it will like just send the instance to tuple to this one, and if it needs to like cross container communication, then it will just send to this stream manager here, and then forward this message to the boat. So basically, that's how the tuples are flowing around within a topology among those containers. So when we talk about back pressure, so back pressure is kind of a mechanism in Heron we designed to handling like traffic surge. So in this case, what happens is the stream manager has kind of a buffer. It monitors a buffer to each instance and to each other stream manager. So once this buffer reaches a threshold or exceed the high water mark of the setting value, you will send the start back pressure signal to all the other stream managers, and the stream manager will will stop the spout from reading outside data into the topology. So we cut the incoming data from at the spout, so that like only already reading data will be continued to be processed, and it will wait. And after once these are processed, it will wait until everyone. So within this with this mechanism, so we are able to handle like very unpredictable traffic, and before the streaming job like crashed or something like that. So basically, that's okay. Yeah, that's kind of the overall overview of the Heron architecture and some kind of important features we have. So next, I'm going. Okay, yeah.
So is there any way to make this problem simpler by using some Kubernetes?
Sorry?
Is there any way to, so this, you implement all this platform,
Mm-hmm.
so can we
Okay, so I
use Kubernetes to
Yeah.
make this much
Yeah. Oh, let me repeat your question. So you're asking like if we can use Kubernetes
Yes.
to solve this
Yeah.
problem easily.
Yeah.
So I would say like Kubernetes is more like a scheduling platform. So if you have some kind of services you want to run, then you can utilize the Kubernetes, and it will help you to handle all those failure cases, right? But here, we are like one level higher on top of Kubernetes. Heron is kind of a computing framework, which to some extent, it's very similar to MapReduce. So what it's trying to do is, first, it wants to simplify the API. So providing a standard API like in Heron, it's like just like Storm, like execute method and the next type of method, so that users can purely focus on their own like application logic. And the second is the failures we are trying to handle. It's not. It's kind of different from the Kubernetes trying to handle failures. Here we are trying to handle the data flow handle. So it's a data path. So Kubernetes is responsible for if your service is down, right? So what happens? So so if the data here is not correct, then I don't think Kubernetes can help a lot here. But if, like, say, these instances, these processes are down, or this whole container are not working, then I think Kubernetes can help in this situation. So we are aiming, though they are all like called for tolerance, but it's kind of different level stuff. Okay. So no question? Okay. Yeah. So I think now Ning will give some introduction about how Twitter is using that and other stuff.
Thanks. Yeah, my name is Ning. I'm a teammate from Nong. Our names are similar, just a one letter difference. A little confusing. So I'm going to talk about the Heron in production in Twitter, like inside Twitter. Just one note is this slide is pretty much similar, pretty much the same from the slides we had in the last meetup, that's 5 months ago about. So some data may be like a little bit outdated, just FYI. How to? Okay. So here are some examples inside like of topologies inside Twitter. Some are fairly straightforward, like merging some two messaging queues and then doing a simple process. Some are more complicated, like process and then like fun out a lot. So that's just the typical topologies. In fact, most topologies are simpler, but we do have a few complicated ones. Heron has a UI, so that's one big component for the Heron framework. So this is an example of a Heron UI for one single topology. So you can see this one is the logical component, the connection of the topology, like the DAG graph of the topology. So 3 input there, and then maybe pre-process, and then merge. Finally, there is an aggregation happening there. And here is basically the physical plan of this topology. Each color matches to basically, I don't know this color to where, but they are categorized by the colors. And these are the containers, so we know we have 15 containers, and we have 193 instances in total. These instances are for all the components. In fact, if you click on each one, it will show the specific instances in the containers. So that's an important feature. Next one here, there are the matrix there. So let's start from this one. So we have 5 major matrix that we collected from topologies, like the commodity and failures, CPU, memory, and GC. And here it's similar, but it's more like a color. So we can see pretty much all the time. They are fairly healthy in this case. After you start a new topology and start the UI, then you have more things to play. So here in Twitter, so finally we have 3 times to 5 times reduction in the resource usage compared to before the migration. So that's a big win, but that's a little bit old. Like a non-site, like a Storm is also evolving. So this is not really apple-to-apple comparison, but just in the old days, the evaluation is after the migration and before the migration.
So Heron is in production at 2 years?
Yeah.
For almost over 2 years.
2 years?
Yeah.
4 years?
4 years. But it's very long. Lots of years.
Right. So there are a few different use cases inside Twitter. Like a non-site, Twitter is more real time. So Heron or Storm, they are kind of make sense for Twitter. But in fact, Heron has a lot more use cases there. So not really for Twitter. Even inside Twitter, we have real-time ETL, that's all like just aggregation and then transfer data from one place to another one. Real-time like business insight, they have analytics for business data there. So spam, everything, spam is, I think it's priority this year, but that's important. So Heron is important as well. Real-time trends, that's like general, like Twitter feature, they have like real-time process. What is happening now, like popular keywords or some event happening. So, and real-time machine learning, we have some simple one to, I don't know them, some teams. So we just support it. And the real-time ops, so the like the operational team, they use Heron to process some like metrics and then monitor the services. So these are like technical use cases. There are definitely more we didn't cover here, but it's just this sounds really for Twitter for tweets. Right? There are many other use cases, and these are like some companies like using Heron or involved in Heron development as well. This one is the Heron is open source project, and Heron now is like donated to Apache, so we are working on making the first Apache release as well. And now it's incubating, so in future we are trying to graduate from there. So community contributions are important for the project. These are the numbers. They are relatively old, outdated, but 5 months ago, so we have like 2,500 commits. We have 80 something contributors, and 10 plus companies using Heron. And we hope more. So these are some examples, like not really from development inside Twitter. This is from community, including like Streamlio, some guys from like Microsoft and some other people as well. These are just some examples. We are working on new things as well. So first one is like Heron equal API. So use configuration to config the topology instead of like writing code. And different schedulers. So we support a community. Like before, it was developed in Aurora, and now later community added like community support Yarn and Mesos Manhattan as well. Also high-level programming high-level DSL. Like Heron itself is like inherit the Storm API. So we user like need to write the spot and the boat, like we saw in the previous slides. And it's logical from like a implementation point of view, but now like functional programmings are pretty popular, and some people at least care more about the functional part. Like we do a flight map, we do a filter, we do some like I don't know, some other things as well, like reduce this kind of stuff. So we have already also like some high-level DSL Streamlit. This is a functional API. This for Heron. And okay, and later we also there is like Scala interface as well, API as well. Essentially, one stateful processing was like developed by the community. It's not really by Twitter itself. So that's good. Self-regulated processing. So we have a monitoring system inside the topology there. So if this Darling detected some issue inside a specific instance, we will try to resolve the problem by block the traffic or restart the container. So the last one, this one is also, we have integration using Apache Blue Paper for the storage as well. That's just some examples of like a community works, and there will be more. If you want to learn more about the Heron itself, on Storm, so we have papers in 2018, 14 and 15. So that's fairly old, but after we work on new things, maybe we have more stuff. This is a little bit outdated, so I will skip. Like I said, like also classic, we hope the community can grow, like more usage, more developers. There are many interested the community can make Heron more successful, and we can solve more problems as well. also like different companies, they have like different expertise or different interests, so they will contribute in different kind of areas. One example is like the Dalian self-monitoring part is mostly worked on by like Microsoft guys and also one of our teammates. So this is right. There's also something in progress. Also, we have some like a proposal about adding the Heron cycle, like a storm cycle support, so you can run the cycle query and then start topology. And there's like a machine learning. We are thinking about how to integrate with machine learning frameworks as well. Okay, thanks. I think that's all our content for today. Questions? We can talk after all the slides, so we still have time. But yeah, feel free to come to us. Yeah. Okay.
So
Thanks. Yeah.
I have a question. So many companies use Apache Storm, Kafka.
Mm-hmm.
So the Heron is some optimization of these two, or integration of these open source, or
Right. Heron definitely works
how does it compare with
with Storm.
Storm and Kafka and stuff?
Right. Kafka is the messaging queue,
Yes.
so it is like for the data.
Right.
And Heron can work with Kafka, so you can have a spot to connect to Kafka, receive data, and write to Kafka. So there are like two different things. For Storm, like Non mentioned, Twitter used Storm before, and we had
So
some.
Twitter is not using Storm anymore.
Right, we all migrate to Heron. They have the same API,
They
so
replace
migration
Storm.
is fairly like switch from one library to another one.
Okay.
And
But
it's
what
super-
about Kafka? Twitter is still using
Kafka,
No.
we currently
No.
use event bus.
No,
Also-
Twitter has its own messaging systems called Event
Right.
Bus. So we partially use some very old version of Kafka, but it's not supported very officially, and we use our own in-house called Event Bus. I don't think it's open source.
I think it
Yeah.
is. Oh, wait, maybe not. Maybe distributed
It's
law.
not,
or
right?
something.
It's not open
Okay.
source, the
Yeah.
Event Bus. So basically, Heron is like reading the data from Kafka or Event Bus,
Oh.
do some processing work, and write the result out to like storage system or messaging systems. And previously, like we used Storm to finish this task, but as my previous slide said, we like met a lot of problems and a lot of like on-call maintenance issues at that time. So we replaced Storm with Heron. Yeah.
So how do you compare with Storm in terms of real-time latency, in terms of real-time features?
So I think like both of the framework, the latency is not a big concern.
Oh,
So the bigger problem is like the stability and the scalability and the efficiency of the resource usage. So that's the things we found. Like I remember, if I remember correctly, so once we migrate from Storm to Heron, like we reduce the internal usage by 30% or even 50%.
Resource usage?
Like CPU and
Reduce 3x.
Yeah, 3x,
300%.
Resource reduction.
300%.
Wow.
I think like in addition to that, I think there's if you look at Heron paper, there's a performance comparison between Storm and Heron actually. Heron is like 10 to 15x faster than Storm. And latency wise 10x faster from a latency also lower. So their numbers are published actually. And then we also added one more iteration of performance improvement. So that got us another 3 to 5x. So essentially it should be 30 to 40x faster, I think, something like that. Yes.
Thank you.
The papers you referred to were a little bit old. Are you planning to publish another one?
So I think we published the paper in 2015. Then we totally, I think like around 4 papers have been published in here. So the last paper was published last year.
Okay.
So like first was the Heron introductory paper, then Heron self-regulating systems, which was published last year. Last year also we published one more paper on the what do you call abstract engine, like microkernel streaming or whatever it is. That is one. Second one, and the fourth one got published somewhere around 2016 or 17. So 16 one paper got published. So there are totally 4 papers. So. And you published blogs also quite a bit. So the blogs might be more latest too. If you go to Twitter engineering twitter.com.
Twitter engineering blog.
Yeah. So,
Is there a more recent comparison of Apache Storm and Heron?
So to be honest, like
Twitter does not use Storm at
yeah,
all, so
we
it's hard
don't
to
use
compare
Storm
it.
anymore, and our customers, they're kind of very happy about the Heron experience. So nobody is mentioning about Storm inside. So we don't like spend much attention on
Well,
that.
let me
anymore.
ask you, what are you concerned about in terms of performance? Maybe that's the, and what dimension are you concerned about performance? In terms of scalability or in terms of what you say?
Maybe I should mention a little bit about my background. I'm a scientist and I
Oh, okay.
recently switched to these kind of frameworks, and these are 2 options and I was trying to make a selection among these 2, and I'm currently using Apache Storm and was considering also Heron at some point.
I think you should definitely try, especially the API is the same, so there's no like extra cost for you to like rewriting all your jobs, right? You just need to change the dependency and compile that.
Oh,
I just want to add one more thing is we did also mention another benefit of using Heron is the operational work is a lot less, because in Heron each process is each instance is in each process. So you have like log, you have like GC CPU usage like we saw in the UI. For Storm, it's harder to debug if there's anything wrong. This is important for Twitter because like many people managing their own topology, and if anything goes wrong, it saves their time if it's easy to investigate. So that's one major thing, because like our data set is big. So yeah.
Yeah. How would you optimize the structure of the topologies?
Optimize the structure of the topology, like from number of bolts to some X number of bolts to like Y number of bolts, right? That is, it doesn't do dynamic optimization, but you could potentially do what do you call? I mean, you can optimize based on what bolts and everything. So, like for example, if you have multiple shuffle grouping, probably you can collapse them into one stage and do one shuffle grouping. That could be a possibility. Again, depends on the logic quite a bit. You need to look at the logic, how it works, and what stage can you remove the stage or whatever it is, right? So, do you have any?
Yeah, so a lot of in terms of optimization and a lot of in terms of debugging, what you really need to do is be informed of the actual performance of your topology in terms of like the stats listed there. In terms of GC, a major problem could be GC, a major problem could be capacity, and those indicators from the stats gives you an indicator of whether you should have more instances of a component or less instances. That's usually the case because this whole, if you think about stream processing, it's all basically queuing theory if you think about it as in terms of that. And what really kills performance a lot of times is because you have some bottleneck somewhere, right? That you have one part of your topology and you're not able to pump the same rate of data into that component, and it's backing everything up. So in that instance, you look at the stats, you look at your queue size, the cardinality of your queue. If it's filled up, I should basically increase the number of instances because I require more processing power to process the tool that I'm receiving. And with the Dalian project that Microsoft came up with, it introduced some basically auto-scaling, elasticity to a topology in which your topology can figure that out by itself and grow and shrink dynamically based on your statistics at that time and your performance. Does that kind of give you an
it makes
overview of
sense.
that?
Thanks.
Yeah, so I just want to add something about this this graph. These graphs are kind of part of the Heron project. So once you set up the environment and you submit topology,
and they will all be shown automatically in the web UI page. And also, these metrics here, like CPU, memory, GC, capacity, failures, they're just a very, very small part of all the metrics we exported. So if you have some other like time series visualization system, in Twitter we call Cuckoo, and I think outside there is a Prometheus, right? So you can connect all the send all the metrics to that visualization part. So you will have a very detailed information of how is your topology working on, like what's the memory usage, what's the CPU usage, what's the GC, and what's the network status, and all those kind of information available there. So
maybe if you are using Heron with Kubernetes, Heron runs on Kubernetes also nowadays. So if you use Kubernetes, then you pretty much you can get everything in the Prometheus, because Kubernetes comes with Prometheus inbuilt. So you can get all those charts and everything. So any other?
How does Heron keep up with the evolvement of Storm? Like, I think Storm has a bigger release coming up. Will the API be adapted then smoothly, or will it diverge in like a year? Or what's the plan on that?
you mean the
I can comment.
Yeah.
So you're talking about Storm 2.0, right?
Yeah.
So with Storm 2.0, I'm not sure when that's actually going to release, even though I'm actually on the board to decide that. But it's always been pushed off. There are a number of big items, but in terms of API, there isn't change. Even starting, if you look at the API, going back to even before graduated top level in Apache and the incubating days, even when it's actually in Twitter, the API really stayed pretty much the same. The only thing that really changed is it changed from com.backtype packages to org.apache package, like the package class name, and that's about it. Like, no one. The thing with these projects is like, if you change the API, it's gonna turn a bunch of people off. Like, there's no way anybody in the Storm community would be for changing the API, because no one's gonna upgrade them. It's gonna break a bunch of stuff, and I don't want to go recompile my code, or I don't want to go change my code to upgrade to 2.0. The API is not going to change.
The functionality wise, I think we are trying to keep to same level. So, like Jerry said, API will stay pretty much the same. And when Storm has new feature, we are going to evaluate like if this makes sense to have it in Heron, how should we achieve the same goal. So if you are familiar with Storm or Heron interface, API is fairly straightforward. A few interface classes, and all the changeable part are from the configuration. So you set this configuration, set this value, the behavior will change. So this API is pretty much the same, and the others we are going to try to keep in sync. Our goal is to have a modern streaming process system, not really just Twitter works okay for Twitter and then it's done. Yeah. Okay. If no questions, your turn.
Thank you, Ning.